Hello, it's Dave Giles here for the next lesson of Cambridge International Education IGCSE Physics. We're looking at the waves unit, and today we're looking at reflection. So I want you to use a protractor to determine the angle of incidence and angle of reflection. I want you to describe the relationship between those two angles, and then describe the appearance of a reflected image and construct a ray diagram to show its formation. So we'll start by looking at how to use the protractor first, in case you don't already know how to use one from your knowledge gained in mathematics. So this here is a normal 180-degree protractor, and you can always use the outside edges, I would say. So you can normally measure to plus or minus 1 degree. So you can go start at 0, 1, 2, 3, etc., all the way to 180 degrees. So this is your baseline. And this here is the crosshairs where the two lines cross. We've got two sets of numbers. We've got the outside numbers and we've got the inside numbers. And it's usually easier to use the outside numbers. So when measuring angles, it's important to know which numbers to use. So the angle is facing to the left this time. We want to measure this angle. So this is my protractor, and I've put it in completely the wrong place. Line up the crosshairs with the angle. So I've got my crosshair here, pretty much exactly where these two angles meet. And I go up and I make sure this should be on 0 degrees here. And this measures the angle. To make sure the line of the protractor is over the base of the angle, the baseline is at the 0 of the outside numbers this time. So use these ones. Put a big blob on there, and that shows the angle is 60 degrees. So when a ray hits a mirror, it changes direction and the ray is reflected. This here is the point of incidence, and normally we draw a normal line, which is a 90-degree line, straight up from the incidence ray. And this, by the way, is a symbol for a mirror. So this is the angle of incidence I, and it's the angle between the incident ray and the normal. This here is the angle of reflection, and it's the angle between the reflected ray and the normal line. So, pardon me, we draw a line from the mirror at 90 degrees from where the incident ray hits, called the normal line. The angle between the normal line and the incident ray is called the angle of incidence. The angle between the normal line and the reflected ray is the angle of reflection. So this here is an example of a light hitting a mirror, and it's about to be before it's reflected off. So this is where it hits the mirror, and this is the normal line. So the angle here between them is known as the angle of incidence. So to measure that, we need a protractor. Put the protractor there. And you can see this here, the crosshair is where the two lines meet. I've got the 0 here, and you notice I've had to flip it upside down so they look reversed, but it is easier that way. And I've gone all the way up to here. This here is the 40 mark. So this here is on just over 45. So it looks like it's about 46. It's quite a thick line, so it is hard to tell. Ideally, you want a thinner line. And we've got an angle of incidence here of 46 degrees. And here's 2 for you to go at yourself. Maybe I'll extend that line. So this here is a little bit easier because I've put the normal on. This one here, you will have to add your own normal. So it might be a little bit difficult, but you can use if you've got a protractor and you do using this on a laptop, you should be able to measure those two angles. And you should get, for this one here on the left, oh, sorry, the one on the left being, have a quick look. 2 seconds. Actually, what I'll do is I will just add a protractor on here. And we can see that it looks like this angle is around about 41 or 42 degrees. For the second one, we need to add a normal line first. Add our protractor on, and we get something around about 51 degrees. I should really extend this line a little bit so it's easier to see. So if you get something like this and it's not quite long enough, extend the line just so you can see exactly where it is. Okay. So moving on to our second learning objective, which is describe the relationship between the angle of incidence and angle of reflection. So here is a ray of light, and you can see there the relationship between the angle of incidence, which is this angle, and the angle of reflection, which is on this side in this instance. So when a wave is reflected, the angle of incidence I is equal to the angle of reflection R. This is the law of reflection and is true for any wave being reflected from a surface. So wavefronts are a useful way of picturing waves from above. Each wavefront is used to represent a single wave. So the distance between one wavefront and the next is the wavelength. The image below illustrates the wavefronts of how they are visualized. The arrow shows the direction of the wave is moving and is sometimes called a ray. The space between each wavefront represents the wavelength, as I already mentioned. When the wavefronts are close together, that represents a short wavelength, and when they're far apart, that represents a long wavelength. So water waves are incident on a reflector as shown on the right. Complete the diagram by drawing the wavefronts as it approaches the reflector and after it hits the reflector. So first step, draw an arrow to show the direction of the incident wave. Okay. Add a normal line. So my normal line is normal 90 degrees to the mirror or the object it's hitting. Measure the angle of incidence I. Law of reflection. This angle here should be the same. Angle of reflection. And then add on your reflected waves. Draw the wavefronts perpendicular to the direction of reflection, reflected wave, making sure the wavelength remains unchanged. So that this distance here and this distance here should be this distance here and this distance between these two should be the same. So let's have a look at some past paper questions looking at the the second learning objective. So a ray of light strikes a plane mirror and is reflected. Which pair of angles must be equal in value? So we know that W and Z will be equal. They are not, however, the angle of incidence and reflection. X and Y are. So W and Z isn't an option anyway. X and Y is. However, W and Z would also be correct if it was on the list. So the answer to this one is C. Question 2. Which row shows the angle of incidence and angle of reflection? Again, it's quite a straightforward one. Angle of incidence is the angle between the incident ray here and the normal line, and the angle of reflection is the angle between the reflected ray and the normal line. So it is Q and R. So the answer is C for this one. Diagram shows a ray of light incident on a plane mirror. The angle between the ray and the mirror is 35 degrees. The ray is reflected by the mirror. What is the angle of reflection? Now, this one here is a little bit trickier because this isn't the angle of incidence. The angle of incidence would be the angle between the incident ray and the normal, which would be here. So this here will be 90 degrees. So if I subtract 35, so 90 subtract 35 gives me 55. So that gives me the angle of incidence, and obviously the angle of reflection is the same. So it's B. And the diagram shows a plane wave reflected by a plane surface, which represents a wavefront. So a wavefront is these lines here, and the one pointing directly to that is C. Now, this wasn't part of the past paper question. However, I have added a little bit of an extension to this. And the extension is, what does B represent? And B represents one wavelength. Okay, so that's the second learning objective complete. Describe the relationship between the angle of incidence and angle of reflection. So the third learning objective is describe the appearance of the reflected image and construct a ray diagram to show its formation. So this here is a picture of the front of an ambulance taken from the UK. You notice the writing appears a little bit strange. And that is so that when you look in the mirror of your car, it looks the right way around. Although I'm pretty sure if you see a big vehicle with the blue flashing lights, you probably should not move out of the way anyway. So you can actually test this yourself. If you happen to have a mirror and you look at this picture in the mirror, you will see the ambulance looks the right way around. So with a reflected image, let's have a look at what changes. So does reflection cause a change, in the following quantities? Amplitude? No. Direction? Yes. Frequency? No. Wavelength? No. And speed? No. So the only thing that is changing is the direction. So I'll show you how to form a ray diagram. So if we look in a mirror, we see an image like this. So this is the word cat. This here is a reflected ray. And in an image, we extrapolate back. So we go back here, we get a T. We go back from this angle. So we take the same line going back, same length as it is here. We get a C and we get an image that looks like that. So the image is what we call laterally inverted. Same size of the object, and it's virtual. Now, virtual just means that it can't be projected onto a screen. So let's have a quick look at some paper 2 questions on that. So a diagram shows a page of a book in front of a plane mirror, and I is looking at the image of the page. Draw a diagram 2 shows a large letter G on the page facing the mirror. What is the appearance of the image G seen by the eye? So looking at the reflected image, you have to laterally invert it, and that will give us this image here, D. Describe which row describes some characteristics of an image formed by a plane mirror. Well, we've already said it's virtual, so we know it's either C or D. And the image size should be the same as the object, so therefore it is D. And question 3, this is the last of the multiple choice questions. I'll move my slightly. The diagram shows an object is placed in front of a plane mirror. The ray diagram shows the reflection of one ray of light from the object by the mirror. Where does the mirror form an image of the object? So the object is here. The image will appear straight in front, and it'll come from this reflected ray. Sorry, the image will appear straight in front of the object, and it'll come by extrapolating back from this reflected ray. So the answer will be A. Okay, thank you very much, everyone. I will be posting the next lesson on refraction fairly soon, and I will also post a link down below in the description. Thank you very much, everyone, and I'll see you later. Bye-bye.